Hi, in this video we will go through the new functionalities in BOSfluids 8, applying them to a cooling water system for a storage tank. So in this presentation we will go through this fire water module and which are the new functionalities like the NFPA analysis, the fire water coverage analysis. Also we will talk a little bit that this module includes the flood and drain analysis, and then we will go through the example to talk a little bit how to apply all of these new features in storage tanks for tank terminals, and later on we will go through the software and we will do a demonstration. So something that is quite common to have in almost all the codes, and that's why we call it NFPA analysis, but this is for almost any code. The reason to call it NFPA is simply because it's a quite common code that is used for fire water, and something that is really common that we have to do is to obtain the pressure at one node of our system that we call the supply node, such that we are able to have the minimum flow rate in the most remote sprinkler. And BOSfluids will do that for us. We just need to specify, as we will see later, the sprinkler characteristics and the minimum flow rates, and the software will calculate which is that pressure. Then the second new functionality is the fire water coverage analysis, and a few things that we can do right now are, for example, we can specify the cone angle and the distance that the cone can reach, and we can see how the spray profile looks like in 3D, which is super useful. And later on we can run the analysis and we can obtain the flux. So based on the pressure that we specified in our supply node, and the software will calculate which is the flow rate at each sprinkler, and with that it will check which is the flux at a given surface that we specify. In this case we have two rectangles representing a floor. And later on what we can do, and this is recommended mostly for dry systems, is to do a flood and drain analysis where we flood the system. As we can see, the blue represents the parts that are already covered by the water. In this case we are showing a given time in our simulation, and we can see how the system is flooded, and we can calculate the forces with this. The red color represents the gas in the system, so as we can see, in many pipes the flow is pushing the gas out and then is being is passing through the sprinklers to the outside. Okay, so now we will talk a little bit about the storage tanks. So something that is quite common in tank terminals where we have multiple tanks close to each other is to have fire water systems and cooling systems. The main difference is that the fire water systems are to shut down a fire or in a specific incident. But when this happens, something that we want to do is to cool down the tanks or the surrounding tanks to avoid a fire in those ones. So we have all these exterior pipes that will inject water to the surface to cool down or reduce the temperature of the surface of the tank and avoid a fire. So we will use the NFPA 15 criteria for this example, and the most important articles of this code are the minimum flux that we need in the surface, which is 10.2 liters per minute per square meter, and also the maximum distance of the sprinklers, which is 3.7 meters. Obviously you will see here that there are distances that are smaller than 3.7, and that's simply because in reality there are obstructions like stiffening rings or stairs, and because of this construction details, we have to change our distances, and we always obviously use smaller or shorter distances than 3.7. One of the key data that we need for this analysis is the sprinkler manufacturer data. Normally, from the manufacturer, what we know is the conical angle, the maximum spray distance of the cone, the minimum pressure and maximum pressure at in the inlet of the sprinkler, and obviously the K factor to know how big is the resistance of that sprinkler. What we see here is the horizontal view, or well, the conical, in this case, top view of a horizontal sprinkler. And we can see that in this case, for a spray angle of 140 degrees, we reach around 0.7 meters. Obviously, if the sprinkler is placed vertically, the distance that can reach is longer than 0.7 meters. So here we can see how we input the data. So the K factor, the minimum and maximum pressure. The reason why we need to input the minimum and maximum pressure is that if we have lower pressures than the minimum or higher than the maximum, we might not have the profile that the manufacturer provides. And then obviously we have to input the minimum flow rate at each sprinkler, which not necessarily is that obvious where we obtain it. So just to explain it, what we do is we multiply the minimum flux or density of water that we need in the surface of this tank times the area that is covered by those sprinklers, the rundown area, and with that we obtain the flow rate. And lastly, we have the spray angle and the maximum distance. So how does the workflow in BOSfluids works after we already input all the data? Well, we can specify which is our supply node, as we mentioned before, and we can run the NFPA analysis. What we will see is something like this, where we have a specific pressure in the inlet, as we can see is 3 bars or approximately 3 bars. And with that pressure, we know that we will have the minimum flow rate at each sprinkler, because the program makes an optimization and checks which is the pressure for the most remote one. So all the other ones will have at least that. And then what we need to check is that the pressure at each sprinkler is above or below the minimum and maximum pressure. We will see that BOSfluids has also nice tools to check that. And if everything is fine, we can simply apply this pressure into our coverage analysis, and we can check simply with that pressure which is the flux at the surface of the tank. As we can see here, we can see the projection of the cone into the surface of the tank. And finally, since our module includes the flood and drain, we can analyze and do this tension study, and we can check how high the forces are, and we can even export these forces into a pipe stress analysis software to do a dynamic stress study. In this case, we can see that the forces are around 10 kilonewtons, which is quite high. So now we will go through the software and we will see how easy it is to apply all of these in this new version of BOSfluids. Okay, now we will go through the software and we will do a demonstration of the capabilities of this new module. So the first thing I'm going to show are the new elements, being one of them the sprinkler. We already spoke a little bit about it, the characteristics that we can add into this type of elements that are based on manufacturer data, like the K factor, the minimum pressure, maximum pressure, minimum flow rate, the spray profile, in this case is conical, and then we have a spray angle and a maximum distance. Then the second thing I'm gonna show is that we have this group of elements of fire, water, being one of them the sprinkler, and then we have these three surface: rectangle, cylinder, and pylon. In this case, we have the cylinder over here. As you see, the way to input this cylinder is by just deciding the length of the element. In this case, it's a vertical length, and the outside diameter. And then we have two pylon elements. One that is here, we made it like this to try to mimic as much as possible the details of the roof. And it's more like, the pylon is more like a reducer in the sense that we decide which are the two outside diameters, the initial one and the final one, and then we have the length. And the same happens with this one at the top. And something we can do is just turn on with this bottom, and we can see the areas. If we turn off the flow model, we can see that only these three areas are part of the area coverage model. So now something else we can do is to turn on the sprite profiles. This is quite useful because then we can see if with this distance of 0.7 all the sprinklers are touching the surface. In this case we can see that it is. But if we go here to the stairs, we can see that we have a loop just to avoid the stairs, and that increases the distance. And when we check that in detail what's going on here, we can see that the distance is larger than 0.7, and that's why the profile doesn't touch the surface. Obviously, if we run this, BOSfluids will be able to check the distance, and it will show zero density of flux of water basically in the surface. But with the spray profiles, we can already check that. So what we did is we group these elements. We made a group called stairs. As you can see, they are yellow. And we can simply, if we turn on the flow model, we can see the elements that are on, and we can simply change the spray angle and the maximum distance. This is usually in the catalogs of the producer, and if we use a spray angle of 100, in this case we can augment the maximum distance to 1.2, and now we can see how we are able to reach the surface, but as we can see, there are areas that are not covered by the conical profile, as we see here, and as we see, for example, here there is this space, and also this one here. So in that case, what we can do, and we have already done it, is we added some sprinklers that are not on in the flow model, but if we just include them, we can see that now we are covering all these areas. And then the flow rates are calculated assuming a run down area, so that the water drains into these vertical parts. Okay, now the next thing is to actually, now that we already have the layout of our system, is to run the analysis. So the first one is the NFPA analysis, and as we mentioned before, we need a supply node, which in this case it will be this one here, is the 9000. So we have already selected this node, and as we can imagine, we will run the model and we will obtain which is the pressure at this point that makes the most remote sprinkler reach the minimum flow rate. And then we have the fire water coverage analysis, and obviously the flood and drain that is included in this module. So let's just run, and we can already check the NFPA and the fire water while the flood and drain is running. So I will turn off the spray model, and let's check a couple of things. So the first one is the flow rate, the pressure. So this is the profile the pressure profile that we will have to reach the minimum flow rate. Above this, we will always reach the minimum flow rate. So with 3 bars in that supply node, we are okay. And now that we know this, the idea is to check, okay, just to be sure, which is the most remote sprinkler. And normally that's not that easy because it actually depends not only on the distance, but also the hydrostatic pressure, right? So it could be that it's one of these because of the height, but it can be also that is one of these or these sprinklers here because of the amount of friction and distance that we have around this ring. We can have enough losses such that one of these is the most remote sprinkler. So what we should do in that case is just select the flow rate and basically go one by one, right? That could be one option, go one by one, checking. As we can see, these ones are receiving less flow rate. This one has almost 125. So as we can see, this one could be the most remote. But the good thing about BOSfluids is that we have an option called relative flow rate, this one here. And as it says here, basically the minimum value of this relative flow rate tells us how far we are from that minimum flow rate. And we can see that these ones here are closer to 0. If we would have a negative value, we will be below the minimum flow rate. So we are above that value. And we can see that these ones have the smallest relative flow rate. So what we thought before makes sense. And if we would have a bigger system, this would be even more useful. And then the second thing that we have to check are the pressures, right? And as we mentioned before, we have the minimum pressure and the maximum pressure in each sprinkler. And if we are between those values, our conical profile will make sense based on the manufacturer. But if we are above the maximum or below the minimum, we will not comply that. So again, one option could be to just select the pressure and go a little bit close to the inlet of each sprinkler one by one and check it, but that takes a lot of time. So happily, BOSfluid has an option, which is this relative pressure. And we can see that, again, we are above 0. If we would have a negative value, that means that we are below the minimum pressure. In this case, we are above that minimum pressure. And if we would be above 1, we would be above the maximum one. So in this case, we have values bigger than 0 and lower than 1. So we are, in every case, complying that. And we can also check that these ones are quite blue, quite close to 0.03, meaning that these ones are the ones that have the lowest pressure. And the red ones here, as we expect, because they are closer to the supply node, they are closer to the maximum pressure, which I believe is 3.8 bars. So if we go here, if we select the inlet 2.1, so almost half of 3.8. Okay, or a little bit more than half. But okay, now that we have said that, the NFPA is fine, and then what we can do is simply go to the scenario, input the 3 bars that we need, and then just run, which we have already done, run the fire water coverage and select here in type the surface analysis. And as we can see, the areas are covered by water. This density has to be at least 10.2 or more. Obviously, in some areas will be more because we have a intersection of different cones, but also it might be that, again, we calculated the rundown area and we expect the water to drain, we have more water. The second thing that is interesting to see is that we have a quite uniform water density. They are not that different between each other, and that's because we selected the sprinklers with higher, as you can see, K factors at the top to uniformly distribute the losses. If we would select the same K factor for each sprinkler, we will have way more water at the bottom because the losses are lower. Okay, so if we have checked this and we have all the areas with the amount of water that we expected, the next step is to check the transient scenario or flood and drain. And we can see, which is a great advantage of this program, the forces on the system. One of the things we can check also is the opening of the valve. As you can see, this is being open in almost 16 seconds, sorry. So in 16 seconds, it goes from being closed to completely open. And we can see how the pressure goes up. We can also just click here on opening and pressure, and we can see how the pressure augments while we open the valve, obviously. But okay, we can go here to gas fraction again, and we can, for example, run and see how the system is filled with water, which is quite interesting to see. Okay, and another thing we can check are the forces, right? And where is the maximum force? So something that we can do is select the min-max plot and search which is the maximum force in the system. As we see, the maximum force happens here, so we can just click on this point, but in time history analysis, and we can see that we have quite a high peak over here that is around 10 kilonewtons. If we go to that moment, we can see that this one has quite a high force. We can see that the pressure, which is the black line, if we zoom in, so there must be some sort of water hammer happening that causes this pressure wave, and that causes the unbalanced forces. So to check that, what we can do is also add the gas fraction. We can see that the gas fraction passes a little bit before, so we will select here. And we will check for now just the gas. So we can see that here, at this moment, when the gas passes through this point, there are not that much forces. But while this continues, there is a moment where these ones kind of have an impact, right? These two different cross sections of liquid or columns of liquid impact between each other, causing a pressure wave. So basically, if we go back to the gas fraction, the moment this happens, right, when we go to pressure, we can see that we have the pressure wave traveling through the system, which is something that physically could happen, that we have two columns having an impact and causing a pressure wave that travels back to the system, which causes these high unbalanced forces. Well, finally, to summarize our tutorial, we will mention the things that we have done today. So we went through the additions to BOSfluids, like the NFPA analysis, the fire water coverage analysis. These two additions are extremely useful for fire water or cooling systems. And then we also went through the flood and drain, we mentioned it. And we did actually a quite nice example. We show a little bit how we can apply codes, how we can use the data from a manufacturer of sprinklers. And we went through the software. We showed that it's a quite simple software to use, and having everything in the same module is super beneficial because not only we can obtain pressures and flow rates based on our necessities, but also we can check if these ones generate high unbalanced loads or not with the flood and drain. Thank you for watching.